I've told you what a heap looks like. Now we want to do something useful with it. And data structures are only really interesting if we can change them dynamically. So in this next subsection, we'll look at the operations on binary heaps that allow them to implement all the priority queue operations. And I'll only very briefly explain the code and then show an example. And for more details, I'll refer you to the extra material on the website. So in particular, I don't want to show detailed code. I think it's, for most of you, it's repetition. And for the others, it's probably too quick either way in the time that I have. But the videos explain this lovely in much more detail. So how do we insert a new element? If we take our heap from before, if you look at this heap and you want to insert a new element, by the severe restrictions on the shapes that we allow, there's only really one spot you can go with a new element, namely on the last level, the next element here on this flush left. So I don't know, I inserted 68. Now, okay, my drawing is not so nice, but this is, of course, the left child of 40. Okay, that's brilliant. So the shape is satisfied. We have a new complete binary tree, just one bigger. But we messed up the heap order because now this one's smaller than this one. So we can't leave it like that. And to conserve this, so this is the other way around. That's bad. Well, let's say it's not like this. So what can we do? Well, if two things are out of order, we can just swap them. Exactly. I think this is too big. I'll try to keep the intermediate stages on the slide. So the first step would be swap the 68 up here, and 40 goes down. That certainly fixes this one. Let me get rid of this blue part here because that's just confusing. Now this is fixed. Now observe that the other child cannot be messed up by this. We still have that the parent is bigger than this child because it already was smaller than the 40, and we replaced 40 by something even bigger. So it cannot possibly violate the condition after that. Okay? And that's important because otherwise we would potentially have an endless number of violations that we create, and so we don't really fix anything. But that's not the case. The other sibling is not a problem in this case. Now we still aren't done because this is not true. So we do another swap. I might just fit or just not fit. You'll have to remember the order. Aw. Ah, cool. I think I created a problem. This one's too far out of the slide that I can't mark it that way, but I can grab it with the other tool. All right. It's not the point to get perfectionist. I also copied the wrong one. Brilliant. So more effort to fix it. So let's see, we had the 40 already down here. We had now swapped 66 to here, and 68 ends up there. And if you check now, all the conditions are fine. This is true, this is still true, and this is true. And now this is also true. Now, see, there's another thing we should think about. When we swap those two, now we did actually put something smaller here, right? That's potentially danger territory. it's still, in this case, fine. Because if you look at what there was at the very beginning, we know that the 66 is still bigger than the 40. So it was fine to put the 66 eventually up down here. And it can't violate any of these links. Because they were fine before. We replaced them with something that's only bigger, so they're fine after. So you see how this is very naturally framed in terms of these precondition postconditions that we talked about for verification. In many cases, data structures have something like an invariant as well. It's not a loop invariant necessarily. It's more something, maybe you can call it a structural invariant. So in our case, we say a binary heap, if you don't disturb it at the moment, must be a complete binary tree, and it must be heap ordered. And now every algorithm that we work with can use this as a precondition. It can rely on this invariant to be in place, and then you can prove correctness based on that. That's exactly what we did. Why are these green inequalities true? Well, because the invariant guarantees them indirectly. Okay, so that's insert. Is this the same problem? No, here it works. I want to comment on this name swim. So people sometimes call this process letting that element swim up the heap, because you basically imagine this was some bubble of air in water, then it would just bubble up the heap. Swim up until to the point where it is denser than the parent, but not less dense. Well, until it has the points in the sorted order of densities. That's how liquids sort, right? All right. That's insert. How do we deal with deleting the maximum? So we've already said it's really easy to find the maximum. Okay, that's the one with the broken 68, but let's just get rid of this again. It's never been there. You haven't seen it. Right. It's easy to find the maximum. It's the 87, no deal. It's in the root. So we can just take it out. And we want to store this in a temporary variable and return it at the end, right? That's all right. But we've created a hole in our fine heap. And holes are not allowed, right? This is, we can't accumulate holes, not part of the invariant. So again, we have to reestablish our invariant. And there's two things that are broken. The shape is broken, and potentially the heap order, well, depending on how that interacts with holes. The first thing is the shape. Let's fix that again, because that's easy. The only way to make the heap one smaller is by removing this slot, right? It's the only way to go. Now, we have this element 25 there, and we have a hole up there. Sounds natural to just do the obvious thing. So let's stick, no, that was not the one. Oh, it insists. Oh, come on. Yeah, what is this? It's always a new bug. Let's try a different tool. That seems to work. Don't ask me why. It's the beauty of open source software sometimes. So let's take the 25 and just stick it in the root. But I guess you can already see that this is not really the solution. At least not the final solution. So the problem now is we repaired the shape, but we again violate the heap order. As you can see here, so this is no longer true, no longer true. So we even messed it up with both children. So what do we do now? We'll have to somehow repair this by swaps again. But we have two children that we could potentially swap this new root with. And we have to be a bit careful because we have to do the right one. So what we do next is we compare the two children. And remember, the invariant doesn't tell us anything. They could be in either order. The bigger could be left or right. We don't require anything. In this case, this one is the bigger one. We want the bigger ones high up. So natural operation is to swap these two. Okay. So let's do that and see how far that gets us. So we fixed this one, we fixed this one. Oh, one too much. We fixed this one, we fixed this one. But we potentially created trouble because we replaced the big element by a small one. And this time the invariant is not going to save us yet. And indeed, we have a violation here, right? So we have to keep going, do another swap. Again, we compare the two children. 25 is the bigger among the two children, so we swap it with that one. Okay, that's not going to work again. Now, in this time, we're fine just because we ran out of children that we could potentially mess up. And that's the usual way how this ends. We just trickle down the heap until we've reached the leaf level, and then there's no more children that could be out of order. The important bit was to swap with the larger of the two siblings, right? That's how we can remove the largest in a heap. The last operation I want to present in some detail, then the rest I'll just claim are similar, is how to construct a heap if you start with a given list of elements. Now, what you could do is you could build a heap from nothing, build an empty heap, and then insert them one after the other. We'll see that this takes n log n time overall. After the analysis, you will be able to see that. For now, you may just believe it. So that's okay, but we can do better. A smarter way is to start with little tiny heaps and use the procedure we've just used in delete max to fix them up into bigger ones. I think this is easiest illustrated again in a schematic example. I won't do the numbers this time. So we take roughly the last half of the elements and put them as leaves of the eventual tree there. I'll just call these little tiny heaps. Each one is a little tiny heap on its own. It has the shape of a complete binary tree. And it's heap ordered because there's just a single node. There's nothing to really go wrong. Now I'll take the next few elements and put them here. And now I'd like to claim that we can make these into little heaps of 3 elements each with relatively little effort. So what we do is we put the element there and we let that one sink down. So we say sink on this one, sink on this one. All the roots are just sinking down once. Now for 3 elements, we can just figure this out in our heads, right? You take the bigger of the 2 children, unless the root already is bigger. So the maximum of these 3 elements is either the root of one of the 2 children. If it's the root, we're done. If it's one of the children, we take the bigger of the one, put them in the root, and swap the root down, and that's all. All right? Maybe a bit quick, but so far that's easy. Now, the tricky bit is that you can do this inductively. So you can put the next 2 elements here and make these into even bigger heaps, again with a single sink. So 1 sink here, 1 sink there. And then you have heaps of twice the size, roughly. Now, why does that work? It works because these parts are already heaps. They're already heap ordered. So the largest of this little heap is in the root. The largest of this little heap is in the root. So the largest of this bigger heap is either this new element or this or this. And so the sink can find that one. If it's in the root, we'll leave it there and we're happy. If it's one of these 2, we swap it with the root and bring the other element down and recursively fix that one. That way, a single sink operation repairs, turns these 2 smaller heaps into one of double the size. And if you do that one last time with the last element, then we have 1 big heap. Now in this case, it worked out nicely because I made the numbers to work out nicely. If you don't have the appropriate number of elements, then some of the leaf parts on the right would be smaller. So some of these heaps are empty, but it doesn't actually change the algorithm. You just merge smaller heaps into bigger ones and call 1 sink. Now the sinks are not for free, and some of the sinks, like the last one, has to go all the way down. So you might wonder if that's any cheaper at all. But it turns out it is, because you can analyze this level by level. I wonder if I can squeeze that on this slide. Oh no. My drawing skills really get in the way today. Doesn't want to. Oh, come on. What I wanted to do is annotate this with the costs. So now we have a little space. If you sum the cost level by level, on the topmost level we do 1 sink. And we sink down, in this case, the height of the final heap. So the cost of the sink is basically the height. In each step, we do 2 comparisons. We find the larger of the 2 children, and we do the swap, and we have to check if the parent is actually larger than the larger child. On the second level, we have 2 times a sink operation, but on a 1 smaller heap, so one less tall. If you go 1 level further down, we have 4 times this, but h minus 2. So we go all the way down, and on the last level, we have roughly n half, and there's a 0 left. At the very last level, we really do nothing. On the levels above, we do 1 or 2. And if you sum up these things, you see that the majority of the calls for sync is really at this low level where they are a constant time. So if you sum this up, that adds up to linear in the total thing. So the overall time is linear instead of n log n. I have that written up properly on the next slide. So let's briefly summarize the analysis I did informally. First of all, what is the height of a tree? I think you have an intuitive understanding maybe, but what I really wanted to mean in this module is the number of edges on any root to leaf path, and I want the longest such path. So you can go from the root, any path down, and you count the number of edges you take. The largest number you can get at by walking down to some leaf. That's the height of the tree. Okay? Which also has, it means a node with just a single tree with a single node has height 0. This one has height 1. This has height 2, and so on. Conversely, we talk about the depth or level of a node as how many edges do I have to go down from the root to reach that element. So this is level 0. That's level 1. That's level 2, and so on. And now you can count how many nodes can I have on a certain level. In particular, if these are full, right, then you have one node on level 0. And for every node on the previous level, you have 2 children on the next level if everything's full. So that means we have on level L, we have 2 to the L nodes if it's full. Right? If you insert 0, then that's 1. If you insert 1, then that's 2 nodes, and so on. So if you sum up the first L levels, and they're all full, that's this sum, which evaluates to 2 to the k plus 1 minus 1. Okay? Almost the next power of 2. So the height of a binary heap can be calculated by inverting this formula in a way. We are looking for the smallest k so that the number of nodes I can fit in with k levels is at least n. That's my height, because I need to put the nodes somewhere. I might have some space on the right, remember, but I need to put in at least n. And if you invert that, it means that the height of this heap is log n rounded down. Remember, height is counting the number of edges, so it actually has height plus 1 levels. Right? You start counting at 0 with the levels. All right, that's terminology. I'm just going over this slowly because we'll use that for other bits. And with that prepared, we can finish the analysis of all the operations. Insert was basically dominated by swimming up. We put the new element in the only spot it can go, and then it swims up. And every step brings the new element 1 level up, or some other element 1 level up. Yeah, here actually has to be the new one. And so after at most h steps, h the height of the heap, we necessarily stop. For deleting, the maximum is the opposite. We sink down. Again, we have h steps of sinking at most, but the number of comparisons here is twice that, because we need to compare the children and we need to compare the parent and the child to see if we're done. And finally, the construction. I've already shown you informally how this summarizes. That's the same sum written up properly. You can write this formally as this sum. And the rest is basically something that you would learn in some discrete math class. So I'll basically skip that here, or pretend that you know it. It's tricks like summing in reverse, pulling common factors out, and then looking up sums like this on some formula sheet. Wolfram alpha is something that's useful for that as well. Last slide is summary of all the operations. If you work out what they work in terms of n, these are the running times for all the operations in binary heaps.